everyone. So yes, as I said, we have two programs going on at the moment. One is on quantum crystals, all the interesting phases of matter you can get with crystalline structures in a mechanical setting. The other one is on nanoassembly, all the interesting things you can make, not from atoms, but things like 10 times bigger than atoms, nanoparticles and beyond. And our speaker, Suri, is part of this nanoassembly program. Last September, we were together at a meeting in Leiden, the Netherlands, in the historic centers of physics, and it was the conference, the workshop, I should say, was on active matter the next 25 years, except it was planned during COVID. So by the time we got to run it, 2 years had already gone past. It was just the next 23 years to get things done. You will see from your brochure that Suri is in the Department of Chemistry, Associate Professor in the Department of Chemistry at the University of Chicago. You've probably heard of it. And some of you might know that like 100 years ago, Dirac said that we now know the mathematical laws, all the mathematical laws necessary to describe physics and all of chemistry. Well, luckily, it's not true. This is why.
Wait, who said that?
Dirac.
Oh, Dirac. Oh.
Dirac. Physicists like to think that everything else is kind of a bit lower level than we are, except for the algebraic geometry, geometers and mathematics. They were sort of a bit up here. Those are the only ones that intimidate us. But chemistry is a very, very lively subject these days. Quite a bit different if any of you did chemistry in high school or later, like I did. It's really quite a different field now. In fact, Jennifer Kahner is the lead coordinator for that quantum crystals program. She gave a talk in the teachers' conference just a couple of weeks ago, and she was talking about atoms and the hybrid orbitals they make. And she said, well, I learned that in chemistry, but in retrospect, it's a lot more interesting. So, this is the physicist attitude of chemistry. But the reason we can have someone from the Department of Chemistry who's really doing non-equilibrium statistical mechanics and physics and all of that, and many chemists in this nanoassembly program, is that it's just physics at different scales. Physics covers all scales, and it's all physics. And at the meeting in Leiden, I heard Suri give a talk on what he's going to talk about tonight, and I thought if I had enough time, that's what I would work on. So that's why it would be a great subject for this evening's talk. Thanks.
Thanks, Mark. For many of the things I'm going to say. So first, I'm from the Department of Chemistry. I went through all the previous speakers here, and without exception, they're all physicists or mathematicians.
Or astronomers.
Or, Peter. So I was trying to think of how I should put together this talk, and how I should introduce the way in which I think about things, to this audience. What I tried to do was I tried to see if I Googled for these three terms, if any popular articles came up. And one thing did come up. This is a New York Times piece that talks about how there is a link between the amount of exercise you do and how well you remember. Now, this is not even chemistry; it's biology. So it's another field. But by the end of today's talk, I'll try to convince you that there's some truth to this in my when viewed through my own lens, and that sort of motivates this title: Active Associative Memory. And I'll introduce as we go through. I'll talk about what these three terms mean, what they mean to me, why physicists should care, why it can contain new physics, and all the fun things one can do with this. But before I dive into that, let me give a small overview of the program I'm here for. And as Mark said, it's the KITP program on nanoparticle assemblies. I put up the full title here: a new form of matter with classical structure and quantum function. This is not a nanoparticle. This is a stack of oranges. So what does this have to do with nanoparticles? Well, it turns out the way the stack of oranges are arranged, they're arranged in a very nice, precise manner. They actually are arranged in a configuration that is the best packing that you can possibly have. Okay? Oranges are macroscopic particles. You can hold them in your hand. They're on the size of a few centimeters. What we want to do in this program, or what one of the main goals of this field is try to see if you can come up with ordered arrangements like this, but not at the macro scale, not on things that you can hold in your hand, but things that are much, much, much smaller. And so the things that one plays with look like this. So this is what's called a nanocrystal. It's not a single atom or a single molecule. It's actually an object that's composed of many, many, many molecules strung together. You see all these hairy objects that are coming out. It's not just a distraction. It turns out that these hairy objects, even though it looks very chaotic, have remarkable properties. And what we think about is how we go from something that looks like this on small scales, scales that are microscopic, and how we can get them to order and form large assemblies. Why is this surprising, or why should this be surprising? If you take objects like this and you imagine watching them under a microscope, the kind of motion they go through is this highly chaotic motion. This was first observed by Robert Brown in the 1820s. It sort of goes by the name of Brownian motion. And Robert Brown famously observed this when he had pollen in water. You observe it under a microscope and you see that on small length scales, on the length scales of micrometers, everything is dynamic. What looks passive, what looks like a passive beaker of water on large scales, suddenly comes to life on small scales, and you see rapid motion, rapid fluctuations. Einstein in the 1900s, 1905, famously wrote down a mathematical description for these kinds of objects, for this kind of motion. It's called Brownian motion. We all understand it well. But the point is that what I want to make is these objects, when the kind of motion they undergo is highly, highly chaotic. So how do we go from this? How do we sort of take this kind of chaos and get large assemblies of this sort? And that ends up being a big puzzle, and that's in part what the field works on. How do we engineer order in such chaotic conditions? It can be done with remarkable effects, it turns out. I've just thrown up this one slide as a slide with open questions on what all can be done. So it turns out in experiments you can actually take individual nanocrystals and you can assemble them into large arrays. Once you assemble them to large arrays, it turns out they almost start behaving like a different phase of matter. They start talking to one another. They start exchanging electrons between one another. And the end result is you actually get devices that you might see in your TVs in the next few years. This is a quantum LED, it's a QLED. Samsung is developing this kind of technology. And this, going from here to here requires an appreciation of physics, as Mark said, on all scales, from the smallest scale of how electrons talk to each other to slightly larger scales of how these particles are jiggling around and dancing around, to even more larger scales where you get device like where you get something that looks like devices. So that's a small plug for the program I am in. What I'm going to talk today has nothing to do with nanocrystals. It has to do with something very different. This is a movie that I grew up with, Finding Nemo. I don't know if any of you have seen it. If you have, yes, great, wow! I'm so happy. So one of the main characters in this movie suffers from short-term. This cartoon movie suffers from short-term memory loss. And the thing that I'm told to talk about is memory. It's a very different kind of order. It doesn't have anything to do with nanocrystals. And very briefly, what I'll show you is I'll talk about how there's physics in memory formation. and recall. It's a very different kind of order, but there is physics that we should all care about. And this is very important physics that relates to concepts, it relates to ideas that we are encountering every day nowadays, machine learning, things like natural language models, all that is contained in the physics that I'll sort of talk about. So that's going to be a large part of the talk. I'll sort of talk about memory and how it emerges. I'll talk about some work that we are doing in this context, some newer work, and then I'll end with some open questions. And again, just stop me if there are any questions. I tend to talk really fast. The last time I spoke slowly was at the top of Mount Whitney when I was oxygen deprived. So that can't happen here. We're at sea level, so if I do talk fast, just stop me and I'm happy to clarify anything I need to. Okay, so what do these words mean? What does memory mean? What does this word associative memory mean? So this is where I come from. I come from the southern part of India. I grew up in a few different places actually. I grew up in a town that's somewhat north of here. You can't see the dot completely, but my family is from deep south, so the way down here. And the southern part of India, especially closer to the west coast of India, like clockwork, every May, June, we have the monsoons coming in. And when the monsoons come in, it's a big event. We don't have rains throughout the year. We have rains in a few months of the year. And at least my childhood, monsoons were an important marker. So much so that when the monsoons, when the first rains hit the soil, the bacteria in the soil release this chemical, and this is the characteristic smell we get from the soil when the first rain happens. And if there's a rainy day in Chicago, which is half the year for us in Chicago, and I happen to smell this, I immediately sort of I remember have memories of the monsoons back home, of where I grew up, and this is a very strong association. And this basic process of having some kind of stimuli, in this case it's a stimuli in our nose, in our olfactory system. This molecule comes in, binds inside our nose, and it evokes memory of rain, vivid images. That's basically what's called associative memory, and it's a very prototypical form of memory. It's the memory that we all have, it's the memory we use to remember things, to recall things, and it's an important part of our olfactory system and of many other things in our body. So this is in cases where you have some kind of binding event that through odors. You can have other kinds of associations that are sort of easier to hold on to. This is a famous physicist from Chicago, from where I come, Leo Kadanoff, and I grew up reading his articles on renormalization group theory, reading all the amazing path-breaking work he did in statistical mechanics. And if you show me a small part of the image, this is arguably a very easy thing to do, but if you show me a small part of this image, I can quickly figure out the person this small part is actually the image this small part actually conveys, and I can sort of figure out that this is actually Leo Kadanoff. And this process is also an associative memory process. We can take small initial stimuli and we can sort of reconstruct figures inside. We can reconstruct figures. We can classify things. So the question that I'll sort of talk about for the next few minutes is how does this happen? What's the physical basis for memory formation, for memory retrieval, and what we can learn by studying associative memory. So I'll take a few detours. I'll sort of talk about systems on a few different scales to motivate the basic ideas. So what I have here is a caricature of a fly, and these are experiments one can do. You can subject the fly to different kinds of odors. You can show the fly different kinds of odors. For some odors, you can associate rewards. For some other odors, you don't associate anything. And you can actually go in and observe the neurons in the fly and see what happens if you keep doing this experiment over and over again. Before you do this kind of an experiment and you observe the neurons, you find that there are some connections in the fly's brain. And after you sort of do this thing over and over again, you actually see that different parts of the fly's brain start lighting up together whenever you show an odor and a reward together, and you start to see that there are more connections that are formed as the training keeps happening. And this basic cartoon is the basis of associative memory. This is a long statement here, and this is attributed to Donald Hebb in 1949, who observed processes like this without a microscope, without complex experiments, and who basically postulated that the way we learn happens in the following way: when you have events in which neuron 1 and neuron 2 keep getting excited over and over again at the same time, there is some biochemical magical process, there's some biochemical mystery that starts to act up, that starts to link up these neurons together. Okay? This rule is now colloquially referred to as the Hebb rule of learning, and this rule, it turns out, is at the heart of how we learn, of how we remember, and how we recall different kinds of how we make associations and have recollections. What I'll do in the next few slides is I'll sort of keep talking about this in different simple contexts and see how we can unpack physics from this, connect it to physics in the first place, and move on from there. Okay? But before that, let me spend a few minutes just talking about how marvelous even the fly's brain actually is. So this thing that I just stated very simply, that the fly has to sort of form associations between different odors and different rewards, it's actually a very complex process. The number of odors, the number of molecules that have odor-like characteristics are a large number, at the very least in the thousands. If you look inside the fly's brain, the number of neurons it has access to make these kinds of computations, to make these kinds of classifications, are actually a very small number, just around 50. Okay? So how do you match these two things up? How do you go from having just 50 neurons to sense different kinds of molecules to actually needing to sense thousands of molecules? So this is a problem, and this almost looks like a computer science problem, because you have to come up with some way in which you classify between good and bad, but you have a very limited a set of things to classify with. So if the fly had access to the internet, and it might still avoid it because it's a web, it doesn't want to fly into a web. But if it didn't, if it actually persevered, it may learn that there are these things called artificial neural networks that have now that we know now how to use, and we know now can actually classify things. You know, you can show an artificial neural network a cat and a dog. And if you show it a cat, it tells you you have a cat. If you show it a dog, it tells you you have a dog. So this is something we know from computer science. How does this fly, which is not a computer scientist, arguably, how does this actually solve this problem? It turns out that the fly has actually figured out a very elegant and ingenious solution to the problem way before we came across it. The solution the fly figured out is actually remarkably similar to artificial neural networks developed for classification. In fact, the first artificial neural network that we developed for classification was in the 1940s. It goes by the name of a perceptron. It was named because it can classify different kinds of stimuli, different kinds of images. And the fly's brain, if you actually look at it closely, ends up implementing a circuit that looks remarkably close to what we came up with in the 1940s. So how does the fly do it? Just a very quick overview. The fly, the input here is the odors the fly gets in.
Wait, is it
Yeah.
just one layer?
Over here,
Yeah.
in the fly's thing. So this is a very simplified caricature of what the fly does. I'll show you a slightly more expanded caricature in a couple of minutes. this, along with a few other modifications, is all the fly needs. It's effectively one layer, but it needs a few more things on top of this. Okay, but that's a great question. Yeah.
Can you amplify when you say layer, just to be clear to the audience?
Yes. I'm going to go into all those things now. Okay. So these are my input neurons. So this is where the fly, this is where the different kinds of odors are sensed. And what the fly does is it has an intermediate layer of neurons that are hooked up to this input layer. The intermediate layer of neurons ends up being a large layer. It ends up having 2,000 neurons. And what this expansion basically allows the fly to do is it allows the fly to pick up very subtle changes in odor responses, and these changes are then computed. They're fed downstream to a different output, and the fly can make the decisions it wants to make. Whether the odor is good, the odor is bad, does it need to fly away, does it kind of stick around? So all those things are sort of done here. But the basic idea, the basic thing the fly sort of figured out is if you introduce a large layer of neurons in the center, and the number of neurons in the center is much larger than the input, it can take any input, spread it out, expand it out, and then it can pick up on subtle differences. And this is exactly what our first neural networks did in the 1940s. Just for comparison, a fly does it in the fly's brain. That's on the order of a few centimeters. This is the first neural network we had. It's called Mark 1. It was a cadmium selenide. It was made out of cadmium selenide cells. And as you can see, it's much bigger than what a fly's brain actually is. So this is just a small.
What's the scale of that?
Of this thing?
Yeah.
This is as big as the door there. So it's a fairly big system because at that point all we didn't have access to. We didn't do electronics. We didn't have access to all that. So it was a very large analog circuit that implemented what the fly implements to classify things. So this is a small detour for me, but I just wanted to put this out there to say that there's actually a lot we can learn from biology. There's actually a lot we can take as inspiration from biology as we build up these kinds of systems moving forward. And just to sort of come back to a question that was asked before, I've just thrown up a more accurate biological representation of how these neurons are linked up. So you have your odor, many odor molecules, thousands of different kinds of odor molecules. They bind to only 50 neurons. They are expanded through a circuit into thousands of neurons. And then they are projected down back onto 30 or 40 neurons, which end up helping the fly decide what it wants to do with the information it has. Just for this question there, this pink thing here is the equivalent of a feedback circuit that the fly implements, and this feedback circuit allows the fly to classify odors very efficiently. So that's the extra thing that I didn't show in the previous thing. So this basic kind of diagram is actually there's a lot here that I won't go into. There's a recent article that was basically inspired by the neurobiology of a fly olfactory circuit, and it turns out that if you end up looking inside how this fly olfactory circuit operates, and I have in bold the important parts from this paper. It actually performs natural language processing, and it performs it using only a fraction of the resources and a shorter amount of time than some of our best neural networks can today. So there's a lot to unpack here. There's a lot biology can teach us. I won't be talking about this, but this is fascinating for me because it sort of opens up new areas of physics, new areas. This sort of poses new questions. How does this happen? What kinds of new mathematical physical structures we can write down? And this is just an area of very active research. Okay, so this is a small detour. Let me go back to the question that I posed: how can we remember, or how do we remember, and how much can we remember? Okay, so let's go back to this partial image of Leo Kadanoff. And let's say the problem I set out for myself is I want to figure out how, if I am presented with this partial image, how do I end up reconstructing the full image of Leo Kadanoff? So that's the problem I set out for myself, and I want to understand that. Since everything in us, all the computations happens through neurons, we'll actually try to map this image onto this very simple neuron pattern. I have two kinds of squares. Squares that are white are neurons that are off. In a more technical term, they're not firing. Squares that are black are neurons that are on. Okay, so I'm just mapping this entire image onto a set of neurons. And what I want is some kind of a process that takes this input. It turns on one more neuron such that I get the right kind of output. So that's what I want. I want to see how this kind of a process can be accomplished, because if I accomplish this, it sort of provides a mechanism for how we can remember. There's the next question of how much we can remember. We'll get to that later, but we can sort of focus on the first thing first. Okay. All right. So and that would be a way to sort of think about associative memory. So to fill in the gaps here, we'll go back to what I showed you a few slides ago, related to how in the fly, as it is learning things, new kinds of neuronal connections keep getting built up, new kinds of connectivities form depending on what kinds of training you put on the system. And the basic upshot of all this is that the biological upshot of all this is that the state of a neuron is determined by the state of the nearby neurons and how they are connected to each other. So this is something that biology gives us. This is the prerequisites biology actually ends up giving us. You can have two kinds of connections. You can have positive connections in which a firing neuron allows a neighboring neuron to fire. You can have negative connections in which a firing neuron inhibits a subsequent neuron, a nearby neuron, from firing. Okay? So if I wanted to go from this kind of a neuron pattern to a neuron pattern in which this is also firing, what I could do is I could set up this kind of a connectivity in which these two neurons are linked up with a positive connection. This, and everything else is linked up with a negative connection. And what this will do is, because this neuron is firing, this neuron will fire. This neuron is not firing. It's a negative connection. It will also cause this neuron to fire. This neuron is not firing. It's a negative connection. It will also cause this neuron to fire. And so on the whole, if you have these kinds of biological rules and this kind of link up, you can get this output state where this neuron fires, and this is the kind of image we wanted to actually get out of the system. We wanted to sort of have this notion of memory. So we start with this input and we get this final output. But I've actually said a lot of words. This seems like a very laborious process to sort of think of how to cook things up, how to connect these things. It turns out it's actually not very it's actually not very laborious. So again, if I have an image like this that represents this kind of a pattern, what you can do is you can do what we do to remember things. We do to learn things. You can train over and over again. You can keep showing this pattern to our eyes, to our brain, over and over again. What Hebb taught us is that if you keep showing this pattern to us over and over again, neurons that end up firing together get wired together. Okay? And so this kind of a connection automatically ends up building up as you keep training the system, and the neurons, because these neurons are firing together, they get wired together. These neurons are not firing, they get wired in a negative manner, and this sort of naturally builds up. So if you keep training, you can build up the kind of connectivity you need such that inputs of this sort end up naturally giving you the right kind of outputs. So that's one of the main takeaway messages that I wanted to sort of convey in the first part, that you can take, the way you can remember is you can keep trying to, you keep seeing the same information over and over again. This kind of a connectivity gets built up over and over again, and then you remember, and then you can, if you're provided with an input that is a partial input, you can recollect everything you want to recollect. Okay? I have not talked about any physics at this point. It's all just an appreciation of the neurobiology that exists and how one can remember. Yeah.
Place cells.
Yes.
So, are you going to get to that, or should I ask my question?
Go ahead.
Okay. So, in graduate school,
Yes.
I would hike a lot, and I had a friend who would never get lost no matter how new the trail was. And I only later discovered this trick, which is he would always look back as we hiked, if it was coming back on the same trail, to lodge in his brain the image
Yeah.
of our return.
Yeah.
That's why he never got lost. And then 30 years later, I learned about place cells, which is the notion that you register some memory.
Yes.
He was doing that,
Yes.
unintentionally or intentionally. I've never asked him. And so, how does this relate to that notion of capacity for the brain to acknowledge that you've been somewhere? This is visual. This is
Yes.
not based on odor.
Yeah.
Visually.
Yeah. So let me come to capacity. So that's the next thing I'm going to come to, and then we'll come back to place cells. We'll talk about how much you can remember, what kinds of limits
But
we'll place.
is this exercise?
It's also relevant for that.
Is this exercise you talked about the generation of what is notionally called a place cell or not?
This exercise can be related to what happens in our cerebellum also, which can be related to the place cells. I think, if I'm not completely mistaken, but this is very closely related to what happens. This is very closely related to how many parts of our brain actually learn. So it's not just the olfactory system; it's actually a broader mechanism for how we learn, for how we get trained to remember things. I'll come back to the question of capacity a bit later, and I'll try to address that. Okay, there's another question somewhere here. No. Okay. Okay, so this is, I've gone through this process. I've said that things get wired together as they fire together, and so this allows us, for instance, to store one image. If I want to store this image, I train, build up the connectivity that I want to build up, and that's that. But what if I now have many images? What if I want to remember not just Leo's face? What if I also want to remember a cat? What do I do? Well, if I just sort of believe what if you just believe what I told you previously, we can try to do the same thing. We can take this image of a cat, see it over and over again. We can build up new kinds of connections. Now, the cat and Leo's face are very different. So presumably the connections you build up here are going to be different from the connections you build up here, and so we may be fine. We may be able to remember the cat and remember Leo's face without much of a problem. But what if I throw in another famous scientist's face? What if I throw in Einstein's face? We can try to do the same thing. We can look at this face over and over again. But now, after we have looked at a cat, and after we have looked at Leo's face, in your context, it would be if you're going hiking, you can look at different waypoints in your hike, and you can sort of keep trying to remember what those waypoints are. This is the analog of that, and you can try to do that. You can train. But now we run into a problem because this face and this face are similar. The kinds of connections you need to exactly remember this face are going to be similar to these connections, and so there may be some issues. There may be crosstalk because what might end up being a necessary connection for us to remember Leo's face might not be a necessary connection for us to remember Einstein's face. We might need some other connections. And so the question that comes to the heart of associative memory from a physics context is, if this is how biology actually learns, how does it manage to do all this? How does it manage to learn image 1, image 2, image 3? There is a lot of crisscrossing connections that get built up, and so will this actually work? We sort of know it will because we do learn like this. But unpacking this mystery is something that requires a lot of physical insight, and it turns out that this kind of a learning process, where you learn this first, then learn this, then learn this, actually ends up working remarkably well. So in other words, if you actually do this kind of a experiment and you keep training, and you start off with an initial pattern of Leo's face with very good accuracy, you can actually recover the entire pattern. And you can do this experiment on a computer, you can do this experiment in model systems, you can do this experiment in contexts in which you can actually see the recovery happening. I won't go into how those things look like, but you can actually do these things and you can see that this works remarkably well. But it only works up to a point. If you get too greedy If, for instance, I have in my brain I have n number of neurons, and I want to remember a billion faces with my brain, with my n number of neurons. It turns out it doesn't happen. The crisscrossing neurons, the misfiring neurons, at some point break everything, and what happens looks like this. You want to remember this, you start off with this thing, and you see segments of Einstein. I think you see segments of cat here also, and you see all kinds of other things showing up. And this is a canonical way in which we tend to forget things. We tend to we mix up our memories, and that happens in general in a very simplified context because we have this rule for learning, and this rule for learning only works up to a point. It depends, and after a point, if you get too greedy, and if you don't build up more neurons, if you don't have a larger brain, we can't end up doing this kind of a thing. Okay, so this is all very qualitative. I've showed you, you go from here to here, but what is this point? How do we quantify it? So it turns out that you can actually draw out a very sharp boundary between how much you can remember, or between regimes in which you can remember well and regimes in which you don't remember well at all. What I have on the x-axis here is the number of patterns that you want to store divided by the number of neurons you have access to. The bigger your brain, you can store more patterns. The smaller your brain, you can't store as many patterns. My child is now 1.5 years, and for him at this point, every kind of an animal is a cat. And every kind of a car is a bus. So he has a small brain. Hopefully this will change in the next few months. But as the number of neurons increase, we can start to learn more. We can start to learn more complex things. The really remarkable thing about this is that this pattern is a very sharp transition. You go from here to here in a very sharp way, and this sort of tells you. This line tells us the capacity of a system to actually remember. There are a few more things I'll talk about. I'll say about this, but before that, I'll add one more axis to this picture, which is that everything that we do and everything we encounter, we are dealing with fluctuations. We're dealing with neurons. We're dealing with cells that are very small, that are subject to all kinds of random forces. And so this picture that I talked about, where the firing state of this neuron is determined by the connectivity, is not exactly right. There are also errors, and these errors are because you just have noise in everything that we encounter. There is noise in biology, there is noise on small scales, and we can't get around that. And so what happens due to this noise is you end up losing out more and more as this noise increases. We can capture this noise the way noise is typically captured, using something that looks like a temperature. And what I'm going to plot here is something that is basically the analog of temperature, the temperature that we all know and love. And the kind of diagrams, the kind of qualitative regimes one gets for systems that have associative memory then looks like this, where as you have more and more noise, you start to lose memory more and more. And at some point, if your noise is very high, you don't have any recall, you can't store anything. And then there's this kind of a boundary that sort of separates memory recall from regions without any memory recall. This transition, this line here between having a memory and having no memory, it actually resembles in some ways the kinds of transitions you have when you boil water. You go from water to vapor. So that transition, where you have a boiling transition, where you abruptly change from one phase of matter to another, it turns out that this kind of a transition, where you go from a region with memory to a region without memory, is also a similar kind, not exactly the same, a similar kind of abrupt transition, where you go from a state where you can recall things to a state where you can't recall things. The mathematical physical insight behind this has occupied people in a field called statistical mechanics, the field invented by Boltzmann for many decades now. This insight was first provided by seminal work by John Hopfield in the 1980s. Many others have contributed to this area. The Nobel Prize in 2021 for complex systems, one half of it was for techniques used to uncover the nature of this phase transition and to solve for diagrams of this sort. That was given to Parisi. And we now have a sense through all these physical tools, we have a sense of what this transition looks like and how much you can store and what kinds of trade-offs one has to encounter. Okay, but the simple takeaway in all this is that there's a biologically plausible mechanism for memory storage and retrieval. If you're below this kind of a capacity, the mechanism is very elegant and simple. It just requires that we build up connectivity between neurons, and if you do that up to a point, you can remember whatever you want to remember, and after a point, you end up losing everything. You end up losing access to all the information that you have tried to store in there.
So,
yeah.
Is it discontinuous? You present it as it's not. There's no partial function.
So okay. So it turns out that this line here up here, this actually is a continuous transition way up here, and this almost has the nature of a critical point, a standard critical point. As you come down here and here, as you come down more and more, the transition you have is almost a discontinuous transition, and it's a discontinuous transition. You go from a region where you have memory, and this thing that I've not labeled is actually a region that looks glassy, and so you go from a region that you have memory to a region where your neurons end up behaving like they were a glass.
So does it bother you that isn't what we experience?
So that's a great question.
At least I don't experience that.
So these kinds of models, the phase that you get here is a phase in which you have imperfect recollection. Mathematically, it's referred to as a glass phase, but this phase is basically a phase where you sort of mix up memories. You get bits of different kinds of memories mixing up. That's what you get here, which is not too far away from the kinds of things one experiences. We end up misassociating things, and that's sort of what happens in this region over here. Okay, so if you're below the original, if you're below this capacity, you can do you can sort of use this biological rule, and you can do a lot of cool things. You can take images, store them, start up with very, very noisy versions, and still end up recovering everything we want to recover. And so you can all this the kind of physics that goes into this kind of recovery is all contained here, and it all sort of starts off with a similar kind of a biological rule. And just to sort of throw this out there, there are actually these ideas end up being relevant even in fairly modern uses of neural networks. So you all might have seen this thing that's in the news now, ChatGPT. So this is a language model. You can ask it questions, it gives you answers, and it turns out that the way ChatGPT actually does all its magic is contained in diagrams like this, is contained in connectivity of the sort that I talked about. It makes associations, it retrieves things. It just has a lot more built in that it's able to store. It's able to store a number of patterns that's remarkably high, but that's the same basic physical element that's sort of that's contained here. So what I did yesterday was actually after I wrote this slide, I wanted to ask ChatGPT what it thought of this sentence, and so I asked. So the actual prompts are slightly different. I've modified the actual prompts. So first I asked ChatGPT, is ChatGPT based on associative memory? It wrote back saying no, it's not based on associative memory, and then it sort of gave me a long answer saying it's a transformer and XYZ. So then I wrote back saying, so this is a technical term, ignore. So Hopfield is one of the people who came up with the physical model for associative memory. So I wanted to give it a prompt, and I said, is ChatGPT a modern Hopfield network? And it said, no, ChatGPT is not a modern Hopfield network. And I thought, oh, I should not have the slide. It's probably wrong. So then I did one more thing, and I said, I told ChatGPT, no, you're wrong. And then I asked it, have you read the paper, Modern Hopfield Networks is all you need? It's a very recent paper, and ChatGPT must have encountered in its training. This paper was written in 2020. ChatGPT came out now. The answer it gave was really surprising. I've never seen anything like this. It said, I apologize for my previous response as I was not aware of the paper. At the time I provided the answer, I have now read the paper less than a second later, and I would like to provide a revised response. And it went ahead and it agreed with me after that. Yes. So.
How did it end?
So it actually so the revised response was it agreed with my assertion that ChatGPT is a form of associative memory, but I had to provide this prompt. I didn't investigate it further. I didn't sort of try to trip it up by saying no, I changed my mind. I don't think it's related. I didn't do that yet, but it's. The revised answer was that it agreed with me that ChatGPT is a form of associative memory. So it actually it had a long-winded answer where it said, oh, in this paper they sort of found these kinds of theorems, and so for those reasons I believe it's a form of associative memory. But all this happened in a second, going from few seconds and going from here to here. So it's a really remarkable advance, the kind of things these things can do. But fundamentally, the ideas are contained in pictures like this, in pictures of associative memory, in pictures of building up connections, in pictures of in this picture of building up an initial signal into a full-fledged response. So again, the actual prompts are a bit different. I said a few more things to sort of help it along. I used the word modern, I put quotes around it and everything. But that's a very small differences. All right. So what I'm going to talk about now is the last few minutes is I'll talk about some recent work we did with this with this setup, and we focused a lot on this line here, and on something that I said, which is that as you add noise, you end up losing memory, you end up losing how much you can store. So mainly noise is treated as a hindrance. It's something that no one really talks about. It's just you add noise, you end up losing information. It sounds so intuitive that we just dismiss it and that's that. But the question we were trying to ask was, can we actually, because noise is an unavoidable component in everything we see, it's there in biology, it's there in chemistry, it's also there in physics, can it be harnessed? Can we use it? Can we put it to good use in some way and do something better? Can we sort of get to regimes where we have the same connectivity, the same neurons, try to store the same information, the same number of images, and have the same notion of how fluctuated the system is, how chaotic the system is, but actually get a lot more out of it. So can we do that? And if we can, it opens up some avenues. It sort of tells us that we can actually go beyond the existing paradigms for storing information, for retrieving information. It may have connections to biology. It may have utility even for artificial neural networks. And that's the question we tried to ask. And we were motivated to ask this question because of a very different branch of physics called active matter. Active matter is a fairly new branch of statistical mechanics, and I'm going to spend the next few minutes talking about what I find some of the most striking implications of what this word active means in active matter, and then we'll come back to memory, capacity, and all those things. Okay, so if I take a grain of pollen in water and I watch it under a microscope, as I said, it's going to fluctuate around, and this is what Robert Brown saw, this is what Einstein taught us. And if I take this beaker of water and I heat it, I'll get it to boil, I'll get it to form bubbles, and I can do all that. So that's the behavior we know. So this is normal matter. Let me now sort of throw up something from experiments that were done in 2013 at NYU. This is really, really fascinating, which completely turns the story on its head. So the experiment I'm going to show you is going to have a bunch of these kinds of spheres. Okay, this thing is not very clear, but this is a polystyrene bead. It's about a micrometer long. It's about a micrometer in diameter. It's a few micrometers in diameter, and sitting up top here, the small black dot is a catalyst, and this catalyst is very special. If you put this polystyrene bead in a particular chemical solution. The chemical solution is hydrogen peroxide. We've all now been through COVID, so we know what hydrogen peroxide is. It disinfects everything. But if you put this catalyst, if you put this polystyrene bead in hydrogen peroxide, in a solution of hydrogen peroxide, and you turn light on with a certain wavelength, it turns out to need blue light, this catalyst decomposes hydrogen peroxide into hydrogen and oxygen. How do I know all this? I'm in the chemistry department, so I get to learn all these kinds of things. Sorry, joke. So that's what happens. And what happens if, as this decomposition event happens, is that this single polystyrene bead almost behaves like a boat with a motor. So imagine taking a boat, having a motor behind. It's going to get propelled for some time. If the motor is a very dumb motor, it doesn't have a rudder of any sort, the boat is going to turn around. There's nothing that stops it from turning, and the motor and the boat just turn, and then it gets propelled for a length along that direction. It turns again, and that's what happens. Okay, so this, in comparison to this kind of motion almost looks like the Brownian motion we observe, just that these particles end up moving along a direction for a certain amount of time. They persist, and then they rotate and they move around. It seems like a really small change. You're not changing much. You're only changing how the particles move. It shouldn't change anything. However, if you take this system and you take a lot of these polystyrene beads, put it in a beaker, shine light of the right wavelength, what happens is remarkable. Again, just to remind you, as you shine light, you have a chemical reaction. It's a very exothermic reaction. It releases a lot of energy. So you're actually heating up the fluid as you're turning on light. Okay? And what ends up happening, if you do that, is this. The system crystallizes. It forms a crystal. It actually freezes when you heat it. And when you turn light off, everything goes away. It sort of behaves like a normal fluid. You turn light back on, it will crystallize in a second. You'll turn light back on now. No. There it is, and then it crystallizes again, and it forms what they call the living crystal. So you can sort of go back and forth. So this is a really remarkable thing, where you have now freezing, not by lowering the temperature, but you have freezing by heating, as opposed to going from water to water vapor by heating. Now you go from a liquid-like state to a solid-like state by heating. And this is the hallmark of this new branch of soft matter physics called active matter, counterintuitive phenomena of the sort, where you can control the states of matter in ways that you would not have anticipated from our typical understanding, and you can get these new emergent phases. There's a lot we can do with this kind of a thing. So just to recap again, this is our conventional notion that you have a solid, you heat it up, it breaks down, forms a liquid. In the active matter, where you have this microscopic chemical reactions, you actually do the opposite. You actually heat it up, and you end up freezing it. And all this seems to result from just a small change. You go from this kind of a motion to this kind of a motion, where you persist along the direction in which you're moving, and then you reorient. This is not just this doesn't just happen in the context of these kinds of synthetic experiments. You can actually also watch this in cells. You can take bacteria. Bacteria, it turns out, have a motion that looks a lot like the motion of this particle here. Bacteria, as they try to search for food, they run in one direction, they tumble around, then they run in a different direction, they tumble around again. And if you take a bunch of bacteria and you put them under the right conditions, you actually get them to form this kind of these kinds of crystalline objects. So each thing here is a bacterial cell. The movie went off very quickly. I apologize, but each of these things is a bacterial cell, and it sort of forms a nice living crystalline material. So this active matter field has taught us that by changing, by sort of thinking carefully about the nature of noise, by going from this to this, you can actually get new phases of matter. You can get new kinds of phase behavior. You can do a lot of stuff with it that I won't talk about. There have been at least 2 KITP programs on active matter, one in 2014, one in 2020, that went into all the amazing physics, all the amazing material science, all the amazing chemistry we could do with this new kind of material. That's almost like a living material. But we are going to we asked a very different question. can we sort of take this insight and go back to memory and get neurons that remember better if they're active? And that brings me back to the original thing that I started off with. Can I actually have better memory if I'm active? If I have neurons that are active. So what do I mean by this? How do I unpack this? So we'll do things exactly the same way as we did before. We are going to try and store many memories. We're going to do the same kind of training, and I'm going to store one last memory here that just reads out Chicago, the name of the city I come from. And we're going to set up the connectivity in exactly the same way. We're going to use this rule to train things, and so that the system remembers. What we're going to do is we're going to set things up such that this whole system is the number of memories you're trying to cram in is at this point over here. Okay, so it's at a point where ideally we should not get anything. The system should forget everything. There should be multiple overlapping wires crisscrossing each other, and it should not be able to remember any of these things. It should be all lost. And what I'm going to show you is if I make the neurons active, and I'll tell you how I do that in a second, and it's just a play on the kind of noise that this neuron experiences, then something somewhat remarkable happens. The canonical picture is we have a noise source for each neuron, in which just like Brownian motion, at each instant of time you have errors, but the errors are completely uncorrelated. If you make an error now, it doesn't have any bearing on what happens in the next instant of time. I'm just going to modify that by saying that there is some persistence. If you make an error now, you'll more likely make an error in the next time step. If you don't make an error now, you'll be less likely to make an error in the next time step. That's the only kind of change that I'm going to put into the system, and sort of changing the kind of noise these systems get, motivated by the phenomenology this new field of physics has discovered, or has taught us about, called active matter. And what happens with this kind of thing is the following. If I start here, I have stored a pattern. I'm going to focus on one pattern. I've stored this pattern in both cases. In the usual case, if I start off with this pattern, if I start off with a slightly degraded version of this pattern, and I do a computer experiment where I sort of see how well these neurons actually remember, quickly it forgets, as we expect. There's a lot of crosstalk, there's a lot of fluctuations. So quickly it forgot what it's supposed to remember, and it lost everything. It just degrades into a mess. It degrades into noise. The same thing with a noise source that has the same temperature, the same notion of how much fluctuations are there, but it's just a bit different. It actually ends up remembering it. You've hardly seen anything move in this image because there was a small defect. It got rectified very quickly, and the system almost has perfect recovery. It has perfect memory in this regime. It actually has perfect memory in this large extra regime here. How do we understand this? What more can we say about this? It turns out that the way we understand it is similar to the way we understand how this kind of active matter, how these kinds of transitions happen in active matter. We basically think neurons get frozen into a memory state for reasons similar to how you get freezing-like transitions here. And the way to mathematically or physically explain this requires us to go back to theories that Parisi wrote down, and that's how we did that, and we sort of get these kinds of new phase diagrams. I see Lars is already up. I think I'm almost out of time, so I'm basically going to end. I just have a couple more things that I can sort of skip in the interest of time. But the main thing that I wanted to convey is that you can take insight from the physics of active matter to get to things that look like improved associative memory. I hope I've conveyed what physics can do for associative memory and what associative memory can do for physics. There's a lot of things that one can learn, and there's a lot of open questions. related to strategies that biology can use to remember and forget things on demand, potentially by changing how noisy or not noisy things are. And some of these things have been observed. So it turns out neurons end up having oscillations that help them form long-term memories, and these kinds of things can be done. More broadly, one can ask questions about how active matter can enable new strategies for addressable memory and classification. So I'll stop there. Thanks so much for your for listening, and I'll take questions if any.
Sorry, do you literally think something like that's going on in our brain?
Like this active thing? So that's something we are now thinking about. So there are a couple of hints that dynamics does actually play a role. So you can study this in model organisms like Drosophila, and you see that as long-term memory is formed in these organisms, the neurons end up having dynamical behavior that has a very particular characteristic, and they can use the dynamical behavior to store information better than when they don't have the dynamical behavior. So it's not just the wiring, it's actually a bit more than wiring that helps the formation of long-term memories. So that's something that we are looking at right now, and we're trying to see what we can say about that. This is just the main takeaway is that if you think about this part that's completely ignored and use ideas from this new branch of physics, there may be opportunities there, and it seems to really exist in some context. Yeah.
Yeah, in the early part of your talk, you talked about recognizing this frontal picture of Leo Cadenov.
Yes.
And by establishing certain connections.
Yes.
But even if that's the only picture you ever saw of him, you immediately recognize him in profile or frowning instead of smiling and so forth.
Yes.
How is it?
Yeah. So what I didn't talk about. So I talked about a very simple form of associative memory in which you really have the full. You end up having perfect recovery or nothing. But what you're talking about is this notion of generalization. So let's say you have seen a picture of Leo Cadenov smiling, and I show you a frowning picture of Leo Cadenov, and you'll immediately recognize that it's Leo Cadenov. In the context of what I talked about, it might seem that that's not possible, but actually the same kinds of architectures I talked about with associative memory, with neurons being connected, with neurons having firing determined by the neighborhood around them, it turns out, surprisingly, it's sufficient for generalization. So it's enough to sort of show you an imperfect image of Leo Cadenov, frowning Leo Cadenov, because that's imperfect for me. So he's always smiling, and you can sort of your mind will immediately sort of classify that as a Leo Cadenov image, and that will happen perfectly. And it's the same physics that I showed you. It turns out. In what I drew out connections just between pairs of neurons. If you end up having connections that are higher order, between 3 or 4 neurons together, you get generalization, and you get those kinds of emergent behavior from the same kinds of ideas here. But that's a very nice question.
Question. You have a question?
I'll ask. Going back to this diagram
Yes.
you're using, it wasn't clear to me when you presented that, and then eventually you showed the Chicago pictures and where the dot appeared there. How much of that was theoretical versus, you pointed out some work with the fruit flies that showed some indication there was some structural changes in the neurons. I'm confused between what is theoretical here and what you've actually measured in the fruit flies.
Yeah, the fruit fly work is so I'm a theorist. I don't work with fruit flies. I should have clarified that at the beginning. In the context of fruit flies, it's a fairly recent development, last 10 years or so, where the entire neural architecture of it has been unpacked. And so this question of how much it can store, its expressivity, its ability to generalize, all those things are still open questions. what we end up working with when we do theory is highly simplified models, because that's the only thing that's actually tractable. There has to be an interface between where theory is and where biology is, and that interface, they're still sort of separated by a large distance. But the hope is that we bridge that gap, because if we do, we'll have new ideas for how artificial neural networks can be built up. We'll have new ideas for how information can be stored and retrieved. Yeah, so I think there's a lot to be done there, but there's a huge gap right now. We work with highly simplified models. So the Chicago thing that I showed you is a very, very simplified model in which I have these neurons, I link them up in pairs, I don't do anything more than that. The actual fruit fly ends up having many, many higher order connections. They belong to the same class, but there's a lot of gap between how much it can store and where we are right now. And one of the papers I threw up there about the fruit fly having the fruit fly circuit behaving like a good natural language processing model, that's a fairly recent work. That's about a year ago from a different group at IBM, where they sort of showed that you can map what a fruit fly does onto a natural language model. So this is all very new, very, very recent work. And hopefully in the next few years, this will be stuff that we can talk about in a textbook, but at this point it's not.
Thank you very much.
Thanks.